So we're going to show some properties of sigma notation here, which can be quite useful to evaluate sigma notation more quickly. So the first one is if you've got the sum from I to equals 1 up to n of k, so k is a number, doesn't rely on a sequence at all, then, so for example it's 2, k is 2. Then what this is really saying is when I is equal to 1, what's the value of k? It's k. When I is equal to 2, what's the value of k? It's still k because it does not rely on I. When k is equal to 3, what's the value of k? Still k. And it's going to go up. Keep doing that. So we get k, and in total here we have n lots of k. So that means this is equal to n times k. Okay, that's the first one. Now let's consider the second one. If we've got k times some sequence that relies on I. So here we have when I is equal to 1, we get k times a1. When I is equal to 2, we get k times a2. We get k times a3. And that keeps going up to k times an. But this is a sum where we can factorize out k. So this is k times a1 plus a2 plus a3 plus all the way up to an. But that thing in brackets is just a sum of terms. It's a sigma notation. It's the sum of ai from I equals 1 up to n. Essentially what this one is saying is we can factorize out the k from the sum, which makes sense. This is a sum. We know we can factorize out a common term. Okay, let's look at the next two. So this is if we've got two sequences being added together within our sigma notation. So let's think what's happening. The first one is a1 plus b1. The second one is a2 plus b2. The third one is a3 plus b3. And that keeps going up to an plus bn. But this is a big addition, so we can actually rewrite the order of this as a1 plus a2 plus up to an, and add on to that the same but for the b's, b1 plus b2 plus up to bn. Because addition is commutative, it doesn't matter which order we do the addition, we can move these around and it doesn't change the sum. But this here is just the sum of the AIs. So it's the sum of the AIs from I equals 1 up to n plus the sum of the BIs from I equals 1 up to n. This is saying if we have a sum within a sigma, we can split it into two separate sums. Now the last one is about how else we can write this, and this links back to things we saw before with there being multiple ways of writing these sequences, these series, in terms of sigma notation. So what is this? Well, this is a1 plus a2 plus a3 plus up to, I'm going to write an extra term here, an minus 1 plus an. But that's the same as a of 0 plus 1 plus a of 1 plus 1 plus a of 2 plus 1 up to a of n minus 2 plus 1 and a of n minus 1 plus 1. But this is the sum of a I plus 1 starting with I equals 0 and going up to n minus 1. Now that was not immediately obvious. The I plus 1 is the fact that this is always the I bit plus 1, and we're starting at I is equal to 0. That's this. And we're going up to I is equal to n minus 1. So this is just enabling us to rewrite a sigma notation in a different form by changing the nth term of the series that's inside the sigma.